Today we're taking a look at section 4-4 on multiplication rule, the basics. And at the end of this section you should be able to first of all calculate the conditional probability of B given A, or the probability of event B occurring after it is assumed that event A has already occurred. Number 2, determine whether given events are independent or dependent. Number 3, apply the formal and intuitive multiplication rules for calculating the probability of A and B. And 4, know when dependent events may be treated as independent ones. Okay, our notation for conditional probability, the probability of B/A represents the probability of event B occurring after it is assumed that event A has already occurred. It is read as the probability of B given A. So that slash represents the word given. Independent events are events where the outcome of the first event does not affect the outcome of the second event. If we have two events that are independent, then the probability of A and B occurring will be the probability of A times the probability of B. So let's look at some examples. Suppose you toss two coins. Would the two tosses be independent? Okay, if you toss two coins, the outcome on one coin in no way affects the outcome on the other. So the answer would be yes. And let me get my pen active here. So the answer is yes. And because of the fact they're independent, we would multiply the probability of A times the probability of B. So in both cases, to get heads, the probability is 1/2. So 1/2 on the first coin times 1/2 on the second coin gives us a probability of 1/4. So that would be the probability of getting heads on both coins. Okay, suppose you toss a coin and roll a die. What would be the probability of getting heads on the coin and a 6 on the die? Okay, first of all you want to think, are these independent? Well, certainly. The outcome on the coin will in no way affect your outcome on the die. So the probability of heads on the coin is 1/2 times the probability of 6 on the die is 1/6, and so the probability of the two occurring together would be 1/12. Okay, number 3, suppose you draw a card from a standard deck of 52 cards. Replace it and draw a second card. Would the two draws be independent? Since we replaced the card, the answer would be yes. We'd have exactly the same set of cards both times. If we had not replaced the card, the answer would be no. But in this case, yes, they would be independent. Okay, what is the probability of getting an ace on each draw? Well, the probability of getting ace on the first draw is 4 out of 13. Since I should say 4 out of 52. Since we return the card, again, it's going to be 4 out of 52. And that is 1/13 squared, which gives us 1/169, just by reducing it to 1/13. Okay, so with replacement, we end up with independent events. So that's something you have to pay very close attention to in the problems. Okay, now in some cases you do not have independent events. What do we do in that case? Well, we actually use what is called the formal multiplication rule. What that says is the probability of A and B is the probability of A times the probability of B given that A has occurred. So suppose you draw a card from a deck and you don't replace it. That means the events are not independent or they are dependent events. Okay, so in this case we have to use the formal multiplication rule, which you can use in every case. So would these be independent? No, because the probability will change once you remove one card from the deck. So the probability of getting an ace on the first draw is 4 out of 52, like we said in the previous one. Now, we make the assumption, it says B given A, so we're looking for the probability of getting an ace on the second draw, given that we did get an ace on the first draw. So that means we removed an ace. There are now only 3 aces out of the 51 cards remaining. Now, I can reduce each of these to make it a little bit easier to calculate. 1 over, I think it's 221. Let me do a quick check. 1 over, I didn't get my 13 in there good, times 17, 221. So you can see how our probability changes when we have without replacement. Okay. Suppose you draw 3 cards without replacement. What is the probability of getting 3 hearts? Okay, so on the first draw, there are 13 hearts out of 52. We've removed a heart, so on the second draw, it's 12 out of 51. We've removed a second heart, so now on the third draw, it's 11 out of 50. And let's see, we can reduce some of these. 3 will go 17, and 4. 4s will go, and I think we're left with 11 over, and I need to multiply this, 17 times 50, 850. Okay. So our intuitive rule of multiplication, and this is basically what I use, or you can use a formal rule, when finding the probability that event A occurs in one trial and event B occurs in the next trial, multiply the probability of event A by the probability of event B, but be sure that the probability of event B takes into account the previous occurrence of event A. So you have to pay attention to the words without replacement or with replacement. Without replacement, your probabilities are going to change. With replacement, they're going to stay the same each time. Now, one last item that we have, which is useful in some cases. If a sample size is no more than 5% of the size of the population, so we're talking about a very small sample, we can treat the selections as being independent even if the selections are made without replacement. So they are technically dependent. So if the sample size is no more than 5% of the size of the population, then you can go ahead and treat them as all having the same probability. So that's very helpful when you have a population, say, of size. Move this so I can have more room. Say you have a population of 10,000 and you're selecting your sample as, let's say, 200. Okay, if we look at 200 divided by 10,000, That's only 2% of the population. Okay, so if you found the probability of someone smoking was 0.0027, and you wanted to know the probability that if you selected two people that you got two smokers, even though you're not technically putting that first person back, you could calculate it this way. And so we get 7.29 times 10 to the negative 6. 7.29. Notice my calculator went into scientific notation. So the e negative 6 means 10 with an exponent of negative 6. So that's equivalent to moving the decimal back to the left, since it's negative, 6 places. So I need 5 zeros. Okay, and notice how small that number is. It really isn't going to make a whole lot of difference that we have treated it as independent, even though they are actually dependent in this case. So that's what that is referring to.